Have you ever stopped to think, what makes an airplane wing so incredibly strong but also surprisingly light?
Or maybe how sports gear absorbs impact without being bulky.
Exactly. The answer, well, it might surprise you. It often comes down to tiny, really intricate structures, things you can't even see, built layer by painstaking layer.
Mm-hmm.
So today we're doing a deep dive into this fascinating world of uh, additively manufactured lattice structures, AM lattices for short.
Yeah, we've gathered quite a bit of cutting-edge research here. We want to unpack how these complex 3D printed structures actually behave under pressure.
Right, and how they're optimized, for peak performance, and also look at some surprising applications where they're already making a big difference.
Our goal really is to give you a shortcut, a way to understand why these miniature marvels are changing design and engineering.
And what it really takes to get them just right. So maybe let's start with the basics. Additive manufacturing itself, AM, often just called 3D printing.
Right. At its core, it's a layer-by-layer, bottom-up process.
So completely different from traditional methods, right? Where you cut material away.
Exactly. That's subtractive. AM is additive. You build it up. And the real power, especially for lattices, is creating these incredibly complex shapes.
Geometries that would be, well, basically impossible with old school machining.
And it's efficient with material, too. You don't need extra tools like jigs or fixtures cluttering things up.
Okay, but it's not perfect, right? There are downsides.
Oh, definitely. Costs can still be high. You can get imperfections in the final product.
And the size, you're limited by the printer bed size, aren't you?
That's right. But the versatility is, frankly, amazing. The official ASTM F42 standard lists 7 main types of AM.
Things like powder bed fusion.
Yeah, using lasers on powder, material extrusion, that's like your typical desktop 3D printer idea, but more advanced. Binder jetting uses a liquid binder on powder.
And they handle a huge range of materials, metals like stainless steel, titanium, nickel alloys.
And non-metals, too. Nylon, ABS, PLA, resins, even ceramics and paper in some cases. It's a broad spectrum.
And that layer-by-layer capability is just perfect for these lattice structures, isn't it?
It absolutely unlocks their potential because lattices aren't solid. They're open-celled structures. Think of a really precisely engineered 3D mesh.
Made up of repeating units.
Exactly, repeating unit cells. And each cell is made of struts, the connecting bits and nodes, which are the joints where struts meet.
Okay.
And the beauty is their properties. They're super lightweight. They absorb energy exceptionally well.
Better strength-to-weight ratio than, say, foams.
Much better, generally, which is why they're popping up everywhere, not just aerospace.
Right. You mentioned biomedical.
Yeah, things like bone scaffolds that your own bone can grow into.
Yeah.
Sports technology, definitely. Personal protective equipment, PPE, where you need lightweight impact resistance.
Okay, so once we grasp what they are, it's good to know they're not all the same. There are classifications.
Correct. The main ones depend on how the unit cells are arranged. You've got periodic lattices first.
That sounds regular.
It is. Same shape, size, topology, all arranged uniformly. A perfect repeating pattern.
Then what?
Pseudoperiodic. Here, the cells might differ a bit in shape or size, but they still share the same basic connection pattern, the same topology.
And the last one?
Randomized or disordered. Just like it sounds, unit cells are randomly distributed, varying sizes, varying topologies.
But for engineering, it's mostly the first two, periodic and pseudoperiodic.
Mostly, yeah, because you can tailor their properties precisely, predict how they'll behave.
Gotcha. And within those, there's another distinction, homogeneous versus heterogeneous.
Right. Homogeneous means all the struts have the same thickness. Heterogeneous means the thickness varies.
Why vary it?
Well, maybe to direct forces or add strength only where it's most needed without adding weight everywhere.
Smart. And people talk about specific models, right? Like BCC or FCC?
Yeah, those are common geometric blueprints. Body-centered cubic, BCC, face-centered cubic, FCC, simple cubic, Kelvin cells. These define the basic unit cell structure.
It's interesting, though, you mentioned despite all this potential.
Yeah, there's still, relatively speaking, a paucity in lattice structure-related literature compared to, say, general AM reviews.
Feels like there's still a lot to uncover.
Definitely. It's an active research area.
Okay, so let's unpack this then. Once we understand what these lattices are, the next big question for designers has to be, how do we make them perform even better? Optimization.
Exactly. And for metallic lattices, mostly made with powder bed fusion, researchers have come up with some really clever stuff.
Like improving existing designs.
Precisely. Take the AFCC, that's an optimized FCC lattice developed by Bai and colleagues, showed significant mechanical advantages over standard BCC, but kept the weight low.
So tweaking familiar shapes pays off.
It really can. Another big finding, across multiple studies actually, is adding vertical struts. Think BCCZ, F2BCC, FCCZ designs.
What does that do?
Significantly boosts mechanical performance, higher collapse stresses, better modulus of elasticity. It's like adding internal reinforcement.
Okay, makes sense. What about weak points, like the joints, the nodes?
Ah, yes. Stress concentration at the nodes is a classic failure point. By et al. Tackled this with the graded strut BCC, GBCC.
Graded strut.
Yeah, they increased the radii, the roundness of the corners where struts meet the nodes.
And that helped.
Big time. It shifted the failure point away from the nodes. Standard BCC tends to fail right at the node. This is a major step for integrity.
Interesting. Any totally new strut designs?
Oh yeah. Ding et al. Introduced the RCH strut lattice, also showed enhanced performance, energy absorption, load bearing, the works, and Cow et al. Showed modified rhombic dodecahedron RD lattices outperform the original versions.
So lots of geometric innovation. What about more advanced techniques, computational stuff?
Absolutely. Topology optimization, or TOP, is a huge one.
How does that work?
It's a computational method. It optimizes everything strut, thickness, length, diameter. It can even remove struts entirely if they're redundant.
All to maximize the strength-to-weight ratio.
Exactly. Get this. Yang and Lai used TOP on a cuttlebone-like lattice. They boosted energy absorption by 174%. Wow. Elasticity by 203%, collapse strength by 142%, compared to standard octet and BCC.
Those numbers are staggering.
They really are. It shows algorithms can find solutions humans might never stumble upon. It's also great for things like biomedical scaffolds.
Okay. Any other big techniques?
Triply periodic, minimal surface, or TPMS. It's another mathematical approach.
It's complex.
It is, but it lets designers computationally tweak volume fractions, structural features, leading to superior mechanical performance, high energy absorption, and you can really dial in the elasticity and porosity you need.
And how do they check if all this works, if the manufactured part matches the design?
Good question. New methods are popping up. There's automated analysis of microscope images to spot manufacturing defects and instrumented indentation testing, IIT, for quicker Young's modulus measurements.
But there was a catch, right, about Young's modulus.
Ah, yes. Crucial point from Larry et al. They found that the Young's modulus measured in lab tests can actually underestimate the stiffness the material shows in real-world use.
So the lab test might make it look weaker than it is in survey.
Or less stiff, yeah. Designers absolutely need to be aware of that potential gap. It's a critical nuance.
Okay, so that's a deep dive into metals. But what about non-metallic lattices? You mentioned plastics, resins. Does everything we just talked about apply there? Or is it a different ballgame?
It's often a different focus. For non-metallics, especially using material extrusion, ME, the optimization often centers more on the manufacturing parameters themselves.
Like how the printer is set up.
Exactly. Dong et al.
Yeah.
Found layer thickness was key for horizontal struts, but fan speed was more critical for inclined struts. High nozzle temperature helped bond layers better.
So tiny changes in the printing process have big effects.
Huge effects. Maslan et al. Found layer thickness alone accounted for something like 67% significance for PLA lattice strength. Process control is paramount.
Okay. Now, you mentioned something interesting, a paradox about cell size.
Yes. This is fascinating. For MIE honeycomb lattices, Pana et al., found that as cell size increases, the elastic modulus and yield strength actually decrease. Seems intuitive. Bigger cells, less material, weaker.
Right. So what's the paradox?
Mason and Liu argued the opposite for other non-metallic ME lattices. They found that decreasing cell size could actually decrease compressive properties.
Wait, smaller cells make it weaker. Why?
Because as you try to print smaller and smaller features with ME, the strut uniformity and quality can decline. You get more imperfections.
Ah, so it's a limitation of the printing process itself at small scale.
Exactly. And that's the opposite of metal AM, where smaller cells often mean better properties because the laser has shorter paths, keeping temps higher, improving fusion.
That's a really important distinction. So optimization isn't one size fits all.
Definitely not. Other things matter too for nonmetals. Strut shape, thickness, surfacing roughness, build orientation, porosity. They all influence mechanics and print time.
And more material generally means stronger, higher volume fraction.
Yes. Maharjan confirmed that higher volume fraction leads to higher compressive strength. Pretty direct relationship there.
Are there innovative ways people are making these non-metallic lattices?
There are. Liu et al. Came up with a snap fitting method.
Snap fitting? Like building blocks?
Kind of. Print the struts and panels separately, then bond them. They found this gave higher energy absorption and compressive strength than printing it all in one integrated piece.
Clever. Any others?
Kumar et al.'s sea urchin lattice, AQ lattice. The cool thing is it allows for supportless fabrication in M.
No support structures needed during printing. That saves a lot of time and material.
A huge amount. And it still offers great energy absorption and stiffness. It's a potential game changer for cost-effective ME lattices.
But print quality is still a hurdle. Shrinkage, accuracy.
Always a challenge. ASME et al. Saw strut shrinkage between roughly 8% and 13%. You have to compensate in the design or adjust parameters.
Is there an ideal layer thickness for accuracy?
Crosley et al. Suggested 200 micrometers produce the most accurate ME lattices in their study. But it can vary.
And simulations don't always match reality.
Tao et al. Pointed that out. Differences between simulation and experiment can come down to things like the actual width of the printed line versus what the software assumes. It highlights the need for really high-quality printers and careful calibration.
Okay, we've covered building them strong, optimizing them. But reality bites. Things get stressed, pushed to the limit. So when these lattices do fail, how does it happen? And what can that teach us?
A critical question for any reliable design. When lattices fail under compression, researchers generally report three main modes.
Okay, what are they?
There's diagonal shear failure. You often see cracks or failure lines at about a 45-degree angle.
Right.
Then there's elastic buckling. The structure bends or deforms, but it can spring back to its original shape once the load is removed.
Like a spring. And the third?
Inelastic buckling. This is permanent deformation. The structure bends, collapses, and doesn't recover.
And how it fails isn't random, right? It depends on the design.
Absolutely. It's deeply influenced by design and post-treatment. Mascri et al. Found failure modes changed just based on cell size, sometimes perpendicular collapse, sometimes brittle fracture, sometimes that diagonal shear.
And treatment.
Critically, they found heat treatment after manufacturing can prevent diagonal shear failure and make the lattice more ductile, less brittle.
So post-processing is really important.
Hugely. Zhao et al. Also linked failure patterns to volume fraction. Different densities failed differently. Some showed ductile dimples, others brittle cracks at 25 degrees.
And they confirmed that nodes are weak points in unoptimized designs.
Yes, failure often initiated near the nodes, highlighting how crucial those geometric details are. Remember Baya's GBCC structure?
The one with rounded corners at the nodes?
Right, that failed away from the nodes. Standard BCC failed at the nodes. It shows how design directly impacts failure location and mode.
What about that RC lattice?
Ding et al. Reported no local brittleness with that one. It failed in a more controlled, inclined compaction. Again, design influencing failure behavior.
Do the individual struts play a big role?
Definitely. Studies by Li, Liu, and others observe local buckling of vertical struts. The specific material and the size of the strut directly control how it fails.
And overall density.
Zhang et al. Linked deformation angle to density. Denser structures deform less overall. But failure can still be triggered by local weak spots, vulnerable nodes, or struts under high stress.
Does the way it was made matter? Like that snap fit versus integrated printing?
Yes, Liu's work showed that. The snap-fitted ME lattices bent without obvious cracks. The integrated ones fractured right at the strut hinges. Different fabrication, different failure mechanism.
Interesting. Any other factors?
Surface treatments matter too. Mason and Liu saw that acetone-smooth structures fractured and bent, but didn't completely break apart like untreated ones. And even just how you arrange vertical struts, as Gumruk and Fadil studied, changes where deformation starts and how failure progresses through the lattice. It's all interconnected.
It really sounds like less like traditional block-by-block engineering and more like playing microscopic Jenga.
Yeah.
Every single piece, every tiny design choice impacts the whole thing.
That's a great analogy, actually.
So this is where it all comes together, right? Every geometric parameter has this ripple effect on performance, especially under compression.
You've absolutely nailed it. The geometric parameters are critical. Take cell wall thickness and auxetic angle.
Auxetic angle. That's the weird property where some materials get fatter when stretched.
Or, in this context, how it deforms under compression. Arjunan et al. Showed increasing both wall thickness and auxetic angle leads to higher compressive strength and elastic modulus.
Okay. What about cell size and strut size?
Krupi et al. Confirmed what we touched on earlier. Generally, increasing unit cell size reduces mechanical performance, but increasing strut diameter and aspect ratio improves it.
Thicker struts are stronger. Makes sense.
Pretty intuitive, yeah. And that holds for ME lattices, too. Strut angle also matters significantly.
How so?
Yanez et al. Found lattices with low strut angles, specifically under 35 degrees, had higher compressive strength and elastic modulus.
Okay, so shallower angles are better for strength. What about porosity? How much empty space there is?
There's a very clear trend. Low porosity means high mechanical performance, more material, more strength.
And conversely, more empty space, higher porosity.
Generally decreases dynamic elasticity and ultimate compressive strength. It's a trade-off. On the flip side, higher volume fraction, which is the opposite of porosity, meaning more solid material, consistently gives superior mechanical properties.
So density is key. Does how you orient the part during printing matter?
For some processes, yes. Mueller and Shea found for material jetted lattices, build orientation, along with buckling behavior and scaling, all impacted performance and print quality.
And getting the dimensions right, making sure the printed strut is the size you designed.
Crucial. Abel et al. Showed that tailored process parameters significantly improved dimensional accuracy compared to standard settings. Standard settings often produce struts smaller than intended.
Which would obviously affect performance.
Right. And finally, there's this really exciting idea Alberti et al. Explored. Heterogeneous designs.
Mixing different types of unit cells within one structure.
Exactly. Combining, say, BCC and FCC morphologies in one multi-morphology lattice. They argue this can lead to higher energy absorption than a uniform, homogeneous design.
Wow, so that really unlocks the design freedom AM offers.
Completely. Creating materials with property combinations that were just impossible before.
Well, this has been a phenomenal deep dive. We've really uncovered how additive manufacturing is enabling these complex, strong, yet super lightweight lattice structures.
Yeah, we looked at how engineers are meticulously optimizing them specific strut designs like AFCC and ARCH, powerful computational tools like TOP and TPMS.
And crucially, we got into how they fail. Understanding that subtle interplay between design, material, and the manufacturing process itself.
So for you listening, some key takeaways are: post-machining heat treatment can fundamentally change how a lattice behaves under load, making it more resilient.
And even tiny design tweaks, like rounding the corners on a strut joint, can give a significant boost to energy absorption and prevent early failure.
Definitely. Also, there's that strong direct link. A lattice's relative density is a primary driver of its mechanical properties. Denser usually means stronger.
And sometimes, surprisingly, a simple chemical treatment after printing can improve surface roughness, energy absorption, and strength, a potentially low-cost win.
Right.
And, it was also fascinating how the research pointed out that using material extrusion, ME, for metal lattices is still pretty unexplored territory.
Yeah, it's mostly powder bed fusion for metals now. ME is typically seen as more for polymers.
But ME is generally more affordable, right? So here's a thought to leave you with. What if we could bridge that gap? Perfect ME for metals.
That could potentially unlock widespread, cost-effective access to these amazing high-performance structures.
Imagine that. Revolutionizing everything from everyday products maybe right up to critical infrastructure. What possibilities could that open up for you, the designer, the engineer, the innovator, creating the next generation of materials?